working for the automotive industry? I don't have the answer yet. I'm actually at the moment conducting a survey on the cluster. So I'm asking companies how many employees you have and how many of them are working for the automotive. But it's expanding all the time. Whenever I go and see the open job opportunities in the companies, there is tens and tens of open job positions, and they are related to automotive. So at least it's growing very fast.
Okay, thank you very much again.
Thank you.
So the next slot is a demo, and the title of that demo is PANORover, Autonomous Driving System Development Platform. The presenter is Marc Zeller, and Marc is Senior Key Expert for Model-Based Reliability and Safety Engineering at Siemens Technology in Munich. His research interests are on the efficient and effective development of dependability-relevant cyber-physical systems using model-based engineering techniques. Marc has over 10 years of experience in different industrial domains such as automotive, railway, and industry automation. Marc, the floor is yours.
Thanks a lot for the introduction, Marcus. So I hope you can now see my screen. And it turns hopefully now big. So today I have the pleasure to present a demonstration which we are developing in context of the Panorama research project together with my colleagues from the Siemens Digital Industry Software in Nuremberg, Olexiy and Norbert. And it's about a small self-driving toy car, a little bit similar to the presentation of the FH Dortmund already before, where we have developed or where we have a hardware and software platform, which is first of all heterogeneous in its nature. And second, it also includes AI as an additional topic. So the aim here of the rover use case is that this self-driving toy car can drive and automatically brake and has a ADAS system which does the collision avoidance. First of all, to detect any object in front of the rover when it's driving, but also especially using a camera to detect pedestrians. And so we have different hardware equipped to that board. We have different sensors like infrared distance sensors, a camera which is equipped, which takes a constant stream of images, and we have an Arduino board, we have a Xilinx board and a Mentor board. And today I would like to especially put my focus on this AI part here, which we have equipped to that platform, and the big question how we can ensure safety of such an AI-based feature. But first of all, I would like to show in a very short video that you get a better impression what this platform is all about. So we have on the first in the center, you see the camera, which takes pictures, and right below, we have a set of 3 infrared distance sensors. We have an Arduino board, which does some low-level controlling, and we have a Xilinx board, which is a multi-processor system on chip for some features, some more sophisticated ADAS features, which you see here. So it has some ARM cores, it has some GPU cores, and it has an FPGA. And this FPGA helps us to have a hardware accelerated convolutional neural network, which we run for the image recognition tasks. And these different boards, which we have here, are connected via a quite simple CAN bus. And also in the future, what we are currently doing is that we extend this with a third board, which is coming from Mentor. It has an Ethernet communication with the rest of the system and will also have then AutoScycling. And here we see how it is running a small rover that you see. It can you can control it with a remote control, and you see if you try to get towards an object, it's automatically braking. See here. So however, how you are driving with this, you cannot hit any roads in the office. So, and here is a very small demonstration running, not in the office, but at home, where you see that we have a camera which then detects here the pedestrians and also avoids hitting them. As I said, so main part here of this demonstration is today about how to ensure safety of such a system. And here we have the specific challenges which we are facing now when we not only have classical software, but also have AI or machine learning based systems. And we have a proposal here where we use the component fault tree methodology, which is an extension of the classic fault tree approach. And the aim is here to track back the influences of a certain hazard on the system level to its causes. So with this approach, we can graphically explain the causal chains of different events which are happening in our system or in specific parts of our system, and which could potentially lead to one of our hazards in the system. For instance, typical hazard would be that we would hit either an object or more severe an pedestrian, which is in our way. So main focus is here that in this approach, we go backwards in our chain from the actuators over our different computational steps to our sensors. And for each of these steps, we will then create a component fault tree element, which encapsulates all different failure modes of that specific component. Yeah? So this is the main difference to a classical fault tree, where we have a fault tree model for each of our hazards, which are then the top events of the fault tree. Here we have one model which encapsulates all that information following the way of image or of information flow, of data flow, or of physical connections within the system. And the big challenge is here that we have on the one side, we have the classical functional safety according to ISO 26262, which we have for years or for decades in automotive. And now with the upcoming AI or ML features, which are equipped in cars, we also have to take care of the safety of the intended functionality, which is the ISO 21448 standard, which we also have to take into consideration. And here we have to ensure that both failures which are happening in our systems and also, in addition, functional insufficiencies, which could, for instance, be triggered in specific conditions, are considered when analyzing the cause relationship of specific events happening and potential failures. So what we have done is that we have extended the CFT methodology to be able to describe cause-effect relationships of both of failures, so traditional functional safety, and of the functional insufficiencies, which we have now when we have AI or ML based functionalities, and which we have to take care of according to the safety of the intended functionality standard. And here in this approach, it's the good thing is that we have just one model where we could equip both kinds of failures in such a model, and then we can do a qualitative analysis for our PANORover system with the CFT methodology and analyze if the hazards are sufficiently mitigated or if we need additional mitigation measures. And so we can combine in the analysis classical functional safety and safety of the intended functionality. So what we have done for our PANORover system, we have created an MBSE model using Capella and the Arcadia methodology, where you see here the different boards, which I have shown in the last video. And if we can also go into that, we can see into more detail, which are the different components, software and hardware, which are equipped in the system, and which informations are exchanged here between those different parts. And so this is the basis for our CFT approach. So we have an integrated safety analysis model here, which we directly integrate as an additional view in our MBSE model at that site, and which you can see here. And we have chosen here basically two hazards. One is the collision hazard, and one is the unintended braking potential hazard, which is more not only safety relevant, but also reliability relevant. And then we have created for the important components in the system, we have created a CFT element each, which we see here. So we have the motors, we have the motor driver, we have our different ECUs, which we have equipped to our PANORover system, and we have the sensors here. And the next step, so we can look inside of a CFT element, and we see that here we describe the cause-effect relationship. So we see the different internal internal failures which could occur, for instance, in this low-level controller unit, and how these failures are propagated via these triangles, the black and the yellow ones, which represent the flow of failures, which we have here. And you see also that we have on an exemplary basis also created here the respective failure rates. So, and here, for instance, if we go into the perception functionality, we see that in addition to the classical failures, we have represented also the functional insufficiencies in the same way as we have presented the failures. And what we can then do is then we can run a minimal cut set analysis and qualitatively analyze which set of hazards can lead to a specific, which set of failures and functional insufficiencies can lead to a hazard. And this helps us to conduct a safety analysis and to ensure the proper functionality of a system, which also includes AI-based components. So that's the end of my small presentation or my small demonstration I've presented to you, and I'm open for question.
Thanks a lot, Marc, for your demonstration. We have one question in the chat. Do you create FTAs, CFTs manually, or have you considered using tooling to create these and calculate other relevant parts like FMEA, like Dymodia, hip hops, and others?
We created these models manually. Yeah, it's a manual process to reason about what is the potential failures which can happen in different parts of the system and how these failures are propagating through the system. But yes, not for this example, including AI or ML components, but for others example, we have also looked in how we can automatically create, at least for well-known parts, maybe from previous project, already the CFT models.
Thank you. Any further questions? No. So thanks again for your demonstration.